Hello, I'm Cynthia Figge with EKOS International, and I'd like to start by thanking Mark for creating this overarching Uber theme for the conference this year. And I'm very honored to introduce James McCarthy. Jim is a professor of biological oceanography at Harvard, and he has also spent the last several decades really focused on climate change. And in particular, he was co-chair of the Intergovernmental Panel on Climate Change for a number of years, has been a reviewer, a writer, and closely involved in this Nobel Peace Prize winning organization. So I'd like to start and ask Jim to tell us a little bit about how he became an oceanographer.
Well, as a child, I was always interested in the out of doors. I was the good fortune of growing up in the Willamette Valley of Oregon, and parents who encouraged my interests. We were often at the coast, and that was an area that was particularly fascinating to me. In college, I discovered that I really didn't have a favorite area of science. And more importantly, each time I got to a boundary, whether it was between biology and chemistry or chemistry and physics, or then I discovered geology, where so much came together, I realized that what was really interesting to me were the boundaries. And so as I thought about a career that could keep me connected with the out of doors, and one that would allow me to work at those boundaries, oceanography had a certain compelling logic to it, and I have never regretted it, because oceanography, in the period in which I've been in this field, has grown from a study of all aspects of the ocean to one of connections between the ocean and the atmosphere, which together give us climate. Climate is strongly influenced by the ocean. And increasingly over time then, as we saw that the connections between the physics of the atmosphere and the biology of the ocean back to the chemistry of the atmosphere, and it is the ocean that really regulates the planet's atmospheric concentration of greenhouse gases, particularly carbon dioxide. So understanding that in the ocean has been an enormously rewarding opportunity for me.
Great, great. So tell us, the IPCC has, along with Al Gore's documentary, received, I think, a lot of attention in the last year in particular, but has been working a long time on these issues. And I thought perhaps you could give us some idea of this organization, how it came into being, and also what its work has been really in the last 2 decades, and some of the outcomes of the recent reports.
The IPCC came into being in the late 1980s, and it was the recognition by governments that they needed a body of scientists who could report to the governments about a collective understanding of how climate was changing, what its impacts could be, and clearly, I say that with emphasis, in the 1980s, climate impacts were largely hypothetical. We'd not yet really seen anything that looked like serious climate impacts. And then a third part to say, well, were we to do something about this, what could we do and on what timescales? I was an author on the first report that reported out in 1990, then involved in the 1995 report as a reviewer, then, as you said, Cynthia, headed one of the 3 working groups. There are 3 working groups for these reports for the 2001 report. So the process is very interesting. We know nothing else like it in any area of science, where the first word, the I word, the intergovernmental word, means that we really are connected to governments, but we're connected in a very loose way. And our connection is through 2 of the UN bodies, the World Meteorological Organization and the United Nations Environment Program. And so they jointly oversee this endeavor. But they are really, their primary role is that of conveners. That is to say that they have a small staff that organizes travel for the scientists, particularly scientists from the developing world. I'll say another word about that in a moment. And the convening power draws together delegations from all the participating nations, nominally 140 or so now. And among those participating nations, they all propose scientists. They propose their leading scientists to be authors, to be leaders of these groups. And then there is some negotiation because, frankly, you could do this whole thing in the United States if you wanted to. It would have no credibility. It needs to have broad international scientific support. And importantly, it must have developing nation support. So about half of our authors were from developing nations. And we couldn't have done it without them in many regards because they brought us, particularly in the climate impacts, an understanding of what was happening in certain parts of the world where the knowledge really hadn't been widely communicated in scientific publications, which takes us back to one of the really fundamental rules of the IPCC. That is, these are not scientists sitting around saying, well, I think this is happening, what do you think? We are looking at the scientific literature, that is the science that has been published in what we call the peer-reviewed literature, the journals that really are the body of scholarship in our field. And as you know, if you've looked at scientific journals, you can read a paper one year and it says something interesting, and then you see a year later someone saying, well, I don't really think that's right, and here's why. So the body really, in its assessing function, makes judgments about how solid the science is. And in that regard, it's little appreciated that these reports are very conservative. To get a large number of scientists to agree to put their name on statements which are meant to be conclusions, what we understand, without all the caveats, which scientists, it's our default. You never want to overstate. Your credibility as a scientist is the most important thing you have. And the minute your colleagues look at you and say, you know what, you have overread the data. You have just drawn conclusions that cannot be supported. It's something that we all avoid in every way we can. And when you err on that side, you know the consequences are large. So one other word about developing nation scientists, I should say. A really important part of this intergovernmental forum is a trust fund in which all the participating nations from the developing world contribute contributions in cash to the UN office that pays for the travel for all developing country scientists. So let me give you an example. The United States would nominate several scientists to be members. So would the nation of, let's say, Kenya. And the United States, having nominated a scientist, if that scientist is chosen, is then expected to pay the travel costs for that scientist to attend the meetings, participate in this work. The scientist from Kenya, if chosen, is then, all of his or her travel is covered by the trust fund. So it's a very important part of this function. And then finally, all these nations send delegations to come together at a final big plenary when our report, having been reviewed twice by our peers, once already by governments, now once again to look at it very critically, and particularly our pithy sort of 20-page summary of a 1,000-page report. And that's a 4-day meeting where we march through literally line by line. So as I chaired this meeting, we would work through the report, we would read a sentence, it would be displayed on screens with track change. The delegate from China indicates who wants to be recognized, expresses concern about the wording, proposes an alternative. The 2 scientists closest to that part of the report are at my side the whole time, rotating as we move through the report. If it made the statement clearer and did not change the science and no one objected, then we would make that change, we would see it go into the report. I'd gavel that sentence and we'd move on. This is I say 4 days, but there are 4 days and 4 nights. We concluded at 2:30 in the morning. And for the 4 years I did this work, this is when my good friends noted that the color of my beard turned from red to gray. So.
That's great. So I think that we've heard there are models, and some of these models say that the business as usual model is a very dangerous path to be on. It's the path we're on, essentially, and that there are other models and scenarios. And if maybe you could take us through and help us understand. And we have a dispensation to show a couple of PowerPoint slides. So.
And thank you for that permission. As I said earlier, scientists are very nervous talking about data without something to point to for fear of being misinterpreted. What this graphic shows is global surface temperature. And on the x-axis here from 1900 to 2000, this is from the 2007 IPCC report that was released just a little over a year ago now. This is the history of temperature change averaged over the planet, globally averaged over the planet from 1900. And I'd be happy to answer questions later. I'm not going to go into it now, and we'll have a session this afternoon as well about how confident we are in, excuse me, I just pushed advance and I didn't want to do that, so thank you, Scott. Not only how confident we are in this increase, but why we think it's particularly unusual, and why we're confident that we know what is causing this increase. So the statement of the IPCC is that most of the warming in the last 50 years is due to human activities. And I'd be happy to talk about this bit of dip here, and then why we believe it's beginning to show a strong upward curve now. So Cynthia, you mentioned the business as usual. That's extrapolating with this upper red band. And what you have here are 4 representative scenarios. And as scenarios, they are just that. They are plausible futures. Each of them has assumptions about demographics. And although they vary a bit in this regard, the numbers are rather like the ones we heard yesterday. By mid-century, it's expected that the human population will be order 9, maybe 10 billion people, but perhaps not increasing much beyond that. Some demographic models actually show it declining a bit. What else is in these models? The projections for development for both the developed countries and the developing countries. And they are, in a sense, politically correct assumptions. That is to say that the developed countries developing at a rate like this do not have the developing countries developing at a lesser rate. They in fact, tend to converge, but they are not, by 2100, there is still a large difference between the economic status of the developing and developed worlds. But the most important assumption is how we fuel that development. So the business as usual assumption assumes that we will fuel it the way we have to date. And in the last 50 years or so, about 80% of our economy is fueled by fossil fuels, globally averaged. So this is where that 80% number takes you. So the warming we've seen to date is here. And you can see that if you move out, and these are degrees C, if you're more comfortable with Fahrenheit, you can double it, and it's pretty close. So you can see that by 2100, it's a much warmer world. These other scenarios, and the IPCC developed more than 50 of these, and these are just representative, show what happens if you bend these curves. Bend these curves in a variety of ways, but the most powerful way, which I think would be obvious if you think about what I just said, to bend the curves is to change the way we fuel the economy. In other words, rather than 9 billion people, what if you had 8? That will make a lot of difference. If you change the development rate a bit, how much could you change it? What you can really change, and this is the source of the problem. It's not simply number of people or simply our standard of living, it's how we fuel it. If you change that, and the models, a variety of models for doing that, the curves bend downward. Now, does this make a big difference? Okay, we've never been here in human history. As indicated over here, you go back millions of years to find a temperature like this on the planet. We've been cooler. If we go back over the last few million years, the roughly 100,000 year ice age cycle, which is well understood, what regulates that, it's been bounded. It's been bounded by an upper and lower limit. What's happening from here forward is we're overshooting and not just going to a warmer world, but we're going warmer by 100 to 1,000 times faster than anything we know from climate history. So let me just give you a couple of examples of difference between here and here. we completed a study last summer for the Northeast states, Pennsylvania on north, using these models with a technique called downscaling, which you can now look to see what it does in a more localized region. We looked at agriculture, we looked at forestry, we looked at human health, we looked at coastal properties, we looked at fishing. And let me tell you that I personally don't like really hot and humid weather. Right now in Boston, in the summer, we have about 1 week that can be over 90. This is average over the last 30 years, about 1 week over 90 degrees, about 1 day over 100. If we move out to 2100 with this scenario, it will be warmer. But let me start with this one. If we're at this one, rather than 1 day over 100, it will be 3 weeks over 100. It will be up to 2 months over 90. On this scenario, it's about 1 week over 100 and about 3 weeks over 90. Now, I would not particularly relish this climate, but I can tell you that this one is one that has enormous implications for human health. It so happens that in the Northeast states, there is less air conditioning in residential properties than there is average for the rest of the United States because we don't have that much really unpleasant weather. Now, let me just say a couple things about what happens to sea level. Sea level is a juggernaut in all of this. That is to say, there are some large uncertainties as to what will influence sea level in the future. But if we take conservative estimates, by the time we move to 2100 at this upper limb, the sort of 100-year storm that brings flooding into coastal areas now, we have well-established USGS as coastal floodplains, 100-year storms. The 100-year storm repeats in Atlantic City every 1 or 2 years. In New York, every 2 or 3 years. In Boston, about once every 10 years. So if you look at those floodplains and see where that 100-year storm goes and realize how devastating that would be to infrastructure, to coastal properties, to tunnels, to our transportation system, this is a very, very big problem. And I won't go into it now, but I can this afternoon if anyone's interested, talk to you about these sectors, what we would see for fishing in New England, what we'd see for agriculture, what we would see in terms of the economic impact. And indeed, in all of this, you can say, well, there should be some benefits, and indeed, one can see opportunities arise in this. I can mention some later. But the overwhelming impression is that the impacts, as we call them, are negative. And I can also say categorically from our reports, the IPCC reports, that the impacts are colossally negative in the developing world. They take on a much more serious character, and I can talk later about why we find that so.
So we've heard, I think, a good reason to be optimistic in terms of many of the speakers in the last day and in terms of technology, but I guess the real question now is what is the real urgency to move? I work with a number of very large global companies, and they're doing incredible things, I think, to reduce their GHG intensity. But if you look in real terms, out to 2012, 2015, their absolute reductions are around 1%. Mark has talked about nonlinear effects and self-reinforcing patterns. So what have we learned really since the most recent report or in the last several years, and how does that inform our sense of timing on action?
Urgency has crept into these messages increasingly. In 1990, the first IPCC report, we had really the first statement in which climate scientists said, the Earth is warming. It's warming in a way that's really unusual relative to climate history. Mm-hmm. But it couldn't be said with great confidence that we knew the degree to which humans were contributing to this. Is it really small, virtually trivial, or is it substantial? We also didn't have any idea as to whether extreme events were changing. So fast forward 5 years to the second IPCC report, it's now clear from the science that the contribution of humans to this is discernible. That was a key word in the report. But it's hard to still say what impacts might be because there wasn't a lot of indication that even with discernible warming, or with warming and discernible human contribution, therefore extrapolating forward, that we would at some point see serious impacts. Now, another 5 years, roughly the period of the IPCC reports. 2001, for the first time, we see global climate impacts on every continent. That is to say, if you looked at temperature and looked at species distributions, egg-laying times, migration times, flowering times, you would see shifts on every continent. And if you looked at the local weather data, you would see that that shift was consistent with a biological mechanism that would expect it to occur in response to temperature, let's say earlier in the spring. And also for the first time, we could see that the pattern of extreme events was looking unusual. So I mentioned the 100-year storm before. We were now seeing 100-year storms occurring at an alarming frequency. Biggest precipitation ever event on the continent. Continent after continent, you could see this happening. On the continental scale, globally, across the world, you could see extreme events beginning to play out in precipitation events and in droughts and in heat waves. So the world is getting hotter. In some areas, it's getting wetter. In some areas, drier. In some areas, wetter and drier, which is not really a contradiction, which I can explain later if someone is interested. So part of something I should have said earlier about these projections is uncertainty about the models, and particularly how the models might work on finer scale. So this is where a lot of improvement has been made. And if you think about the uncertainty of these models, I mentioned number of people, lifestyle, how we fuel that economy. There are uncertainties about the models as well, in large part because we're trying to model a climate which is a climate we've never had experience with before. And you can use today's climate models, start them in 1900, and put what we call the forcing terms in, put volcanoes, put solar variability, put greenhouse gases, put aerosols, and you can reproduce the record of climate over the last 100 years. Many, many climate centers around the globe do this routinely to test their models. Now you go forward, and we're truly in uncharted territory. So as we have seen more rapidly than we thought possible, the impacts materialize. Impacts that not just affect, the timing of flowering, but affect the agricultural productivity, affect the availability of water. Not just interesting things about ecosystems that might be benign, but things that are really affecting human lives and human well-being. So in this next slide, this was a graphic from our 2001 report that shows something that is rather like what we saw a moment ago, and temperature increase from 1900 to 2000. Here's that fan of scenarios moving upward. And this set of panels, I'm going to talk about simply one of these right here, are what we called reasons for concern, or you can think categories of risk or impact. So I said I'll talk about one, but I'll just mention this one. This is where you'd find individual species. So already at 2000, there was evidence that some were being pushed to their limits and might conceivably, with this progression, move from this amber into red, which would mean extinction. And remember, extinction is forever. As we look at climate cycles over the last 100,000 years, as we went from a sheet of ice that covered all of Canada and part of northern United States, a mile thick, to what we have today, were there species extinctions? Hardly any. A few, the large mammals we know went extinct largely because of human pressure, but due to climate, very hard to find a case. Why? Because in the genome of the organisms on the planet today, their evolutionary history their ancestors accommodated these warming and cooling periods. They changed their ranges, they moved north, they moved south. Well, now we're going beyond those ranges because we're moving into a warmer world and compressing habitats, particularly the northern habitats, in a way that they haven't before. So if we look at this final category, you would note that our judgment at that time in something called large-scale discontinuities, and I'll explain that jargon in a moment, we didn't have anything to worry about until we got out here, maybe mid-century under any scenario. One of the elements in this right-hand column was dramatic loss of polar ice. In 2000, there was not a shred of evidence in scientific literature that Greenland could lose ice at an alarming rate. And I would say today that it is an alarming rate. Everything we thought we understood about Greenland, a block of ice that it's about 10% of the freshwater, surface freshwater on the planet. It's a remnant of that ice sheet that retreated north roughly 18 to 10,000 years ago. If it all melts, there's no scenario for this right now, but if it all melts, it's a lot of water. It's 7 meters or 22 feet of sea level. You don't have to melt but a small fraction of that to affect our coastal properties in a very dramatic way. So what's happened since then? Not only with respect to the ice on land, but ice on the ocean, we have seen some very, very surprising effects. This is sea ice in the Arctic. What you'll see over time now is the graph from 1979, which is when we have satellites measuring sea ice. And these are summer values moving forward in time. And this is the pulsing of summer sea ice extent. We'll see a low level in 2005 here, and now 2007. So if you looked at this curve over time from 1979, we have data that go back, but they're not as precise because they're not from the satellites, to 2006. And you were to draw a line through here, whether you took a mean or this lower boundary, it's roughly linear, about 1% loss of Arctic sea ice per year. In 2007, we lost 20%. So here we are in a trend which, we were inclined to think was linear, moving along, just creeping along. And now we're reaching a point where we clearly have serious concern about an instability. The light that comes from the sun is reflected or absorbed by Earth's surface. And of course, ice is a great reflector. So about 90% of the energy coming in from the sun is reflected by ice or snow. Without the ice or snow, 90% is absorbed by water, which then warms more water, warms more land, if it's on land, or either ice or snow on land. And so it's what we call a reinforcing or positive feedback. This is hard to see without knowing this geography, but this is the Northwest Passage. This photograph was taken from satellite last summer. Historically, this should have been called the Northwest Impediment. It is now the Northwest Passage in summer. It's still frozen in winter. So with the loss of sea ice in the Arctic, some would immediately think of great opportunity. You could cut transit time, or distance, let's say, between Europe and Asia in half for the period of the year in which it's open. That route, by the way, is not likely to go through here for a lot of political reasons as well as narrow passages. The route that will be commercially developed is along the north coast of Russia. So what else might happen? Much of the Arctic surrounding land is very low, and there are color shadings here to indicate the stability of the soils. But basically, this is very low-lying terrain. And it's also, we know from where sea ice is retreated, a mention made yesterday of Arctic villages in this area, that these are areas where people have, indigenous people have inhabited the landscape. There's a village called Shishmaref, which I visited last summer here in the Chukchi Sea, where people have lived for 400 years. Their culture, every bit of their sense of place is in this location. 600 people live there now. Their ancestors there for 400 years, and they have to move. Because with the loss of sea ice and the thawing of the ground, the erosion is taking their town into the sea. So thawing through this area, the permafrost, the ground that is permanently frozen at some depth and thaws at a surface layer each year, where we have roads, we have pipelines, we have houses, we have buildings of all sorts designed to be anchored to the solid ice at some depth. We're now seeing that infrastructure being stressed. And as we go forward, that becomes an increasingly serious problem. Other people see opportunity here because of oil and gas reserves. And we know, of course, this is the north slope of Alaska, but Denmark is very keen to explore this area off the northeast coast of Greenland. Some of you may have remembered reading earlier this year the Russian contending that the Lomonosov Ridge really connects to their continental plate, therefore gives them, someone mentioned earlier, the exclusive economic zone, gives them exclusive economic zone that controls much of the Arctic basin. As this area clears, it not only will allow access, but I can tell you as an oceanographer, it will tremendously change the interaction between the atmosphere and the ocean, the exchange of moisture, heat, momentum, which will influence climate, not just of the Arctic region, but the entire northern hemisphere. So let me just say a few more words about Greenland. I could show you lots of pictures, Cynthia made me take them out, of retreating glaciers in Greenland, showing how rapidly these retreats are occurring now. They're retreating faster than ever before, they are thinning. We are definitely losing ice from Greenland in ways that we didn't think possible. It's causing earthquakes on Greenland. Here from 1990, looking forward to 2005, this paper was just published a couple years ago. Look only at the green bars here. These are the number of earthquakes in Greenland. And notice they go from about 5 a year up to something like 25 a year. And if you want to draw a line through this thing, you would say, well, you know what? This is going like this, isn't it? So what's happening? Ice is melting on the surface in the summer. Water is percolating down through fissures in the ice. It's lubricating the bedrock ice interface. Ice is slumping. Blocks of ice slumping dramatically enough on Greenland and then decelerating when they compress to actually shake Greenland. And if you look, as seismologists can, you could sit here in San Diego and with a sensitive seismograph measure these earthquakes. You could also pinpoint its location. Where are they happening? They're right on the paths of the major exit glaciers. So no one thought this possible. And we see now ice is moving on Greenland at rates that were completely unanticipated, not predicted in any climate model at all. If we just fast forward to ask what's happening right now, I have just 2 slides. This is from February, and on the left is the average from I can't read 1985 to 2000. 1985 to 2000 for the ice in the Arctic, and this is determined by satellite microwave imagery. This is the 6-year-old ice in the Arctic, averaged over this period. Here's the 1-year-old ice. Here's February 2008. The 6-year ice is thinned down to here. This is 1-year ice, which means that most of this now will melt this summer. And then just a final slide on this point, I pulled data from just a month ago, from April. This shows the temperature in the Arctic today, and it's comparing it to sort of 1979 to 2007. I think if I can read that correctly here. So, and then looking at today to see, and this is we've got a bar here with temperature. I think the laser is losing its oomph, but you can see the top of the red colors. You can look in the middle of the Arctic here and see red. We can look off Alaska, we can see red, we can see red here. These are 4 or 5, and that's again degrees C, double it if you like to think in terms of Fahrenheit, warmer than average over the previous 30 years. So this is April. These are very fresh data. So what does this portend for the Arctic this summer and beyond and the year after that? It's very likely that we're moving into a new rapid era now of ice loss from the Arctic. The sea ice loss will affect surrounding lands in the way I mentioned and perhaps open up opportunities for commerce and oil and gas extraction. But the loss of ice from Greenland, and notice one of the warm areas here is sitting, here's Greenland right here, is sitting right next to Greenland. it has enormous implications everywhere. Sea level rise isn't just local, it's everywhere.
I was going to ask you, without your scientist hat on, speaking off the record, but I realize both of those are absurd. But knowing what you know, being this close, seeing what you've seen really in the most recent time frame, what do we have to do and when to survive? I mean, really.
Well, I do lots of things not knowing how rewarding they'll be to me. Frankly, I could give a couple of public talks a week if I wanted to. I thought it would be interesting to come here, and I can't tell you how glad I am to have been here yesterday and this morning and to hear about the interest, the innovative ideas for addressing this problem. And I know much of the incentive to move this direction now has to do with cost and the price of oil, but it will get us moving on the path where we need to be. And I can also tell you, talking to the public a lot, they need to hear what you're saying because there is a sense of great despair among many people now who are sufficiently able to look at these information and see, well, you know what? This could be a very different world for my children and my grandchildren, and I don't think I like what it's theirs. So the notion that we have an opportunity here is something that we need to work at. I need to work at in public message. This next graphic shows, I'm going to skip that one and go to the next. A graphic from our early IPCC work, which shows the emissions and their accumulations in the atmosphere as a result of our industrial activities, our fossil fuel intensive activities. And that these emissions are creating impacts that now can be seen across every system and sector, natural systems, socioeconomic systems. And of course we know that just with knowledge of this, some adaptation occurs. We know organisms adapt, but there are limits to that. The polar bear has no option for adaptation once sea ice is gone. And that's why the polar bear was just added to the list of threatened species, because once sea ice is gone, its habitat is kaput. And I can talk to you for hours about the biology of the polar bear and why they won't do just fine living in northern New Hampshire. There is, however, obviously a need for action that is taken here that facilitates the adaptation capacity. And we've heard many examples of that yesterday and this morning. And there's some of that which will require government action, particularly I think in parts of the developed world, but there is an enormous opportunity here for innovation and partnership in the private sector. And if I can just vent one other harangue, I think the Wall Street Journal editorial page has done an enormous disservice to the business community over the last decade or so by continuing to argue there's nothing to worry about here when there is something to worry about and there's enormous business opportunity. So the third rail here really is the mitigation one. That's where we have really not wanted to invest a lot of effort. And we know now, if we go back to my example of the high and low scenarios for New England, that we should take very seriously the need to mitigate, to reduce those emissions that would have us on the higher scenario pathway. But even on the lower one, and if we can bend lower than that, we should, but even on the lower one, we're going to require adaptation. And the more creatively we can think about that, the more prepared we can be, the greater the likelihood that we will diminish in everything we care about, the health and well-being of humans, the preservation of natural ecosystems across the board. So this is really where we need action now. And why do I say now? Well, it's because in this next graph, this is a complicated graphic which shows moving forward in time a couple of centuries. So here's 2000, here's 2100 in here. And here is our emission. We've heard reference to emission terms yesterday and today, and it's often expressed in tons of carbon dioxide. Most of the scientific literature uses tons of carbon. So you'd want to multiply this by roughly 4. Carbon dioxide is molecular weight of 44, carbon 12, to put into units of carbon dioxide, if you're more familiar with that. So here's that business as usual curve. And these curves show what you would have to do in terms of emissions to be in different ranges. So here's a 450 parts per million up here. And that's this center curve that I'm blinking on because I'm running out of juice here. And shows that if you start, within a couple of decades, you're seriously turning it downward, not just plateauing, but turning it downwards, you have a chance by the end of this century, of being on that emission curve. So 450, I can tell you that only a handful of years ago, scientists were timid in talking about 550. It seemed as if that would be so difficult. I teach classes, and you give students assignments, and you look at all the energy technologies, you got spreadsheets, you look at growth and development curves, and you tell students, okay, now you've got a chance to design the world. By 2100, keep global emissions, keep the global concentration below a particular level. If we'd said 450 4 or 5 years ago, most students would have said, can't do it, can't do it. If 4 years ago, in the presidential election, any candidate had said, we must get this nation on a path to reduce CO2 emissions by 80% by 2050, they would have been laughed right out of the political arena. I think one could have argued there was a good chance it would have been locked up as a menace to society, maybe insane, but certainly get them out of the way. Today, the 3 candidates in the race and several others who've dropped out are all saying that. This is what the McCain, Lieberman, now Warner-Lieberman legislation would point us towards. The Boxer-Sanders legislation, both of them kind of in the gold standard range for this, point us towards a 450 target by mid-century. So 450, do we want a world of 450? You know what? We don't know. And as we get closer and closer to 450, and we see successes here, like we did with CFCs, the chlorofluorocarbons, refrigerants. In 1987, it was thought that was going to be so difficult. We'll take baby steps. Successes a few years later, people like Margaret Thatcher said, this is silly, we're going all the way. If you look at, we mentioned yesterday the Clean Air Act and sulfur emissions signed into law by restrictions by the first President Bush in 1992. A trading system set up, was it ever deployed? No, it wasn't needed because innovation kicked in. There was opportunity to make business out of getting sulfur out of stack gas that there hadn't been before. So I honestly believe, now this is just sheer conjecture, I take my scientist hat off entirely, that with those examples, and although this is a much more difficult problem, with successes in this area, that we will be able to do better than what the most optimistic projections are today. Optimistic projections that were unthinkable 4 or 5 years ago. So action now, and again, that's part of why I'm so thrilled by what I've been hearing yesterday and today, is clearly what's needed. If we wait 10 years, if we cycle through a full administration and 2 Congresses in Washington and still have done nothing, we've done nothing for the last 7 years. Frankly, we did very little for the previous 8. If we have another period of 1 or 2 or 3 administrations where we make no progress in this, then I'm very pessimistic about the world that our children, our grandchildren are going to inherit. But if we move aggressively now and begin to demonstrate the efficacy of some of these approaches, then I think there's very good reason to believe, based on all the science we have, that we can bend the curves and avoid a world that will be so different from what we have now that it's not one that is pleasant to think about.
I have one more question, and then I'm going to turn it out to the audience, and so if you can be thinking about your questions. William Calvin, a UW professor, author of Global Fever, says the only thing that's going to get us there is a wartime effort. And I think that's interesting, juxtaposed with the fact that the IPCC received a Peace Prize. And before we open it up, I just thought it'd be interesting to hear your thoughts on how the work that you've done, and we can think about this as a peacetime work for peace.
Well, let me say three things about that. When we completed our report in 2001, our final meeting was in Geneva. And in the following day and a half, I did about 40 interviews with press in Europe, print, radio, TV. And I was surprised, completely unprepared, for how many of the questions were focused on Africa. Now, if you look at all of our analysis for climate impacts, Africa's in the tank. The patterns of hotter, wetter, and drier are all very bad for Africa, very bad for African agriculture. So why was this interest in Africa? The more I heard the questions, I realized that there was a sense among many of these European reporters that environmental refugees, we heard the term yesterday, climate refugees from Africa have only one place to go, and that's north. Go south, it gets skinny, it stops. You can't go east, you can't go west, you go north. And it was interesting to me shortly after that, I was asked to give a series of lectures for 3 years running at West Point, to see that in the West Point curriculum, I lectured to seniors in engineering programs, that they had already worked this into their curriculum. And here's the way they looked at it. The military leaders of this nation tomorrow need to be prepared for the realization that there will be political hotspots, civil unrest, and regional strife in regions we've never had to think about before. And you don't have to scratch too deeply into the history of Darfur to see the role that drought and displacement of peoples played in the conflicts that boiled to what we have today. Or look at Afghanistan, where in the 1970s it was a thriving wheat culture, and now the only sustainable cash crop is poppy. Moreover, these curricula said that not only will we have to be prepared for hotspots, but we also have to be prepared for the fact that much of the world thinks the United States has ignored its responsibility to address its contribution to this problem, and therefore we are in fact making more enemies. And I was really astonished by that. I thought that was so forward-looking and gave me such a respect for the education in our elite military academies that I hadn't really thought about. So, you know, in that regard, I mean, the Peace Prize is usually given in acknowledgement of a handshake or pen and ink on a page, but this was more anticipatory, that if people heed this message, the world will in fact be a more peaceful place. So if we think about how, you know, this could unfold, particularly with serious U.S. leadership, which has been sorely lacking in this area, I think there's an opportunity to position the United States, and particularly with our extraordinary capability in the free market and innovation, in a way that would be really very, very positive.
Thank you. Open it up to questions.
Such a rare opportunity to ask a question like this of someone like you. It's my understanding that as the concentrations of carbon go up, that there's a kind of a bow wave to the effect that the climate we're living in today is largely a result of emissions that were put up into the atmosphere 25, 30 years ago. And that that really increases the urgency of the situation, because even if we dropped everything down to almost nothing, tomorrow we'd still have 25 or 30 years to look forward to based on the emissions that were put in over the last several years. I've never quite understood that, though, and so I would appreciate it if you could just give a little color to that if it's accurate. Thanks.
So the question has to do with the bow wave, we might call it the hysteresis, the lag in response of climate to the changing atmospheric concentrations of CO2. So there are a couple of elements to that. One of the reasons is that carbon dioxide has a lifetime in the atmosphere, what we call it a perturbation lifetime. In other words, you put a burst in, how long would it take for the system to absorb that, to equilibrate, that approaches a century. So the warming, if you wish, that we have bought has not fully materialized because over time, as that warming melts more and more ice, even if you've stabilized emissions today, you will accrue, in the case of sea level rise, from that warming that has not yet materialized. Now, there are two other aspects to it. There are several, but two other that are important. Another is how that energy, that added heat, if you wish, is distributed. And the ocean is an important part of this. The ocean absorbs heat more slowly and releases it more slowly. It's the reason you have onshore and offshore breezes. If you're a sailor, you know how this works. The land absorbs and releases quickly. The ocean more slowly absorbs and releases. So air will rise over land when the land is warming. In the daytime, brings air off the ocean. At nighttime, the land cools and the air blows the other way. So as this mixes into the oceans actually swell the same way the mercury in the thermometer swells when it acquires additional heat. So as you mix this heat deeper and deeper in the oceans can't go down, they can't go out, they go up. And so part of the climate impact that we have yet to experience from the emissions that are in the atmosphere now are the result of the redistribution of the ocean and the effect on sea level rise. Then finally, another factor has to do with what we call the aerosols in the system. And there's a range of aerosols from small particulates, from soot, from sulfur in the atmosphere, sulfur that comes largely from the combustion of coal. There are also natural sulfur vents like volcanoes. And that washes out on a different time scale. So as we reduce, as we are for human health reasons, the sulfur released from human health and natural ecosystem reasons from coal combustion, we reduce the contribution of the atmosphere that actually provides a cooling effect. The sulfur dioxide in the atmosphere that arises from fossil fuel combustion or from volcanoes actually has a reflective property. So as we move forward for all the right reasons, Britain in the 1950s with the killer fogs, Europe seeing what was happening to forests in the 1970s in Northern Europe and Scandinavia, the 1980s, period of serious research, looking at the effect of sulfur, so-called acid rain, in the Adirondacks and in eastern Canada, the Clean Air Act provisions signed, I mentioned earlier, by the first President Bush. As we now move to get more and more of these aerosols out of the production stream, we are owning more of the heat trapping, insulating properties of the greenhouse gases. So these are three important factors that come into play in that sort of lag or hysteresis. And some of them we have some opportunity to work with, like the aerosols, and are making serious efforts globally in the interest of human health and ecosystem health. But others are very much controlled by the pacing of the climate system.
That was a great question. Would you mind stating your name and company? We are recording this.
I'm sorry, Eric Blatchford from TerraPass.
Yeah, hi, I'm Scott Gardner with Advantage Engineering. This isn't my area of technical expertise, but I think like many people here, we end up in debates with people that take an ideological bent about this topic, and we always state that the scientists know what they're doing. These are climatologists, and this is some consensus. But what undermines that, and I wanted to ask specifically about a fellow just across the river from you at MIT, so Professor Linson. So is there a point of capitulation? I mean, where other experts who have credibility finally say, yes, all of these unknowns that I kept stating, they're gone, and now there really is not any credible scientist who would give fuel to this ideological battle.
So the question is about what we call the contrarians occasionally, and I'll make a point of this. People refer to them as the skeptics. Every scientist is a superb skeptic. You're constantly questioning, do I understand this correctly? Is there new information that changes my understanding? This is what science is all about. So the contrarians, unfortunately, again mentioned yesterday, were aided in a significant way by the financial resources of one big company. I testified a year ago, April, before the House Science Committee on the role that ExxonMobil played in really slowing the public recognition of the importance of this problem. Just as with the tobacco company, in fact, part of what our case was built upon was the realization that they had not just morphed the tobacco industry tactics, they'd actually hired some of the same people and the same bogus organizations to produce documents that cast doubt. That was their product, cast doubt. I was in a session with Sir John Houghton with a press interview with Reuters a while ago, and a man from Reuters said, well, I think you're just giving us one side of the story. Isn't there a whole other side? And so he said, okay, let me see. If I can think, how many of the 1,000, let's say 1,000 climate scientists across the Earth, how many of them would disagree the Earth is warming in an unusual way? How many would disagree that humans are now clearly recognized as an important contributing factor to that? How many would disagree that if we continue moving with our economies the way we are, heavily fossil fuel dependent, that trend will continue? How many would disagree that there will be serious impacts as we move into a climate regime with lots of uncertainties, but probably more bad news than good news than we've ever had before? He said, well, globally, maybe 10 out of 1,000. And later I said, where did you get the number 10? And he said, well, actually I could think of 5. I said, that was my number, but he said I doubled it just to be safe. So my colleague Dick Lindzen, used to be my colleague, he was at Harvard and left. He has been a major part of many of these reports. He is the most distinguished climatologist. He's actually a meteorologist, but contributing to climate discussions involved in any of these matters. Dick, if you know him, is a born contrarian, and I tell him this to his face. He does not believe that there is sufficient evidence to link smoking with lung disease. He will sit in any of our seminar discussions and raise questions over and over and over again, expressing disbelief that someone has come to a conclusion about particular data sets. Although he's been part of these reports, his name is on them, he later says, well, I didn't agree with everything. And, you know, Dick is someone who has, it's well documented, been tied to the oil and gas industry in his testimonies and writing documents for them. So, you know, you mentioned him as a singularity in this business. He continues to write papers. There's no Lindzen School. None of his former students, no postdocs have taken this up. There's no one who amplifies his work. He's pretty much a lone voice. But highly vocal. The press loves him. He's always willing to talk.
David Morris, president of EcoVerdants. Thank you very much for scaring us into action. NOAA just had a report out that said that extreme drought conditions in agricultural-based areas contributes significantly to CO2 increases. Can you talk about that and a little bit about agriculture's part in it?
So the question is about drought contributing to CO2 increases. The workings of the terrestrial biosphere is the entire natural and managed system of vegetation on our planet are clearly very much in play in all of this. As you know, plants pull carbon dioxide out of the atmosphere. Plants and all animals, all microbes, all fungi also respire, release CO2 to the atmosphere. And that balance locally is very much controlled by climate. It's controlled by temperature, it's controlled by precipitation, it's controlled by whether it rains X amount over a year, but how X is distributed, if it comes very, very concentrated or more evenly distributed, makes a difference for those plant communities. And we know these patterns across the globe that, you know, if you're a gardener, you know this, you can't just plant any plant in your locality. That local climate very much influences the sort of plant that will do well in those environments. And this is part of the evolutionary progress of enormous diversity that has woven its way into the fabric of these ecosystems. So we affect this in a variety of ways as we as we till the soil, we aerate it, we release, we get oxygen into the soil that causes then the microbes to be more active, to break down some of the carbon, which puts carbon dioxide back in the atmosphere. We know that if we cut a forest and it's replaced by, let's say, grass, that grass will hold less carbon than what was in the forest. So where is that? Well, if we burned it and went off to the atmosphere, then that adds to the CO2 problem. So part of the question about future climate is whether the plants that are successful now will, under a future climate regime, be different. For example, there are scenarios whereby the Amazon dries out to where the Amazon forest can no longer be sustained, to be replaced by grasslands. This would then arguably take all of the inventory of carbon in that forest and put it back into the system, because, or say all the inventory of the forest minus the inventory in the grass, which would be significantly smaller, back into the system. So some of these feedbacks, these responses to drought in certain areas would affect natural vegetation or affect agriculture to a point where there would be a net release of carbon back to the atmosphere. I think we've popped the button here.
That's right. We're now adding to our time.
And thanks for the blue bottle, Mark.
Well, thank you. And we'll be back at it at, I think, 3:30 for more questions. But thank you, Jim, very much for being with us. And
thank you for the opportunity.